So 15th group elements. So these are also very important for your examination point of view, and the elements are in a 15 group are nitrogen, phosphorus, arsenic, antimony, and bismuth. Okay, so the main three important things we need to remember is nitrogen, phosphorus, and this one. Okay, these three other questions will be framed on these three uh, elements. So first we'll talk about the phosphorus. So it exists in two forms, so white phosphorus and red phosphorus. We can say white P4 and red P4. And here we'll talk about white P4. It's having a tetrahedral shape. Okay, so but this compound is highly reactive towards air. Okay, so when it reacts with air, it forms a compound P4O10. So this is very important. So the difference between white phosphorus and red phosphorus is, so white phosphorus reacts very fast with the air and it forms a P4O10, and this doesn't react with air. Okay, this is the difference between the white phosphorus and red phosphorus. They may ask in examination that which phosphorus forms P4O10 upon treatment with the air. So we can simply go for white phosphorus, and the structure of P4O10 also very important. So those things we'll discuss later. And then now, so this white phosphorus this is highly stable up to 360 degrees. Okay, sorry, around 560 degrees, and this is having the structure. If we see the structure, this is having a tetrahedral structure like this. Okay, and the bond angle between three phosphorus, the bond angle between this bond and this bond is 60 degrees. Okay, so it's supposed tetrahedral means it's supposed to be 109.281, but in this case in P4 the bond angle is 60 degrees only. And this white phosphorus, if we heat for several days, so we'll get a red phosphorus. Okay, so the only difference between red phosphorus and white phosphorus is white phosphorus reacts with the air, it forms P4O10, and red phosphorus will not react with air, and it doesn't form P4O10 actually. And this red phosphorus, if we can heat at high pressures, and it forms a three-dimensional structure. So in that three-dimensional structures, phosphorus is arranged in the pyramidal structure. So as of now, till now, the important points are, these are not that important. The important points are white phosphorus and its exists in tetrahedral shape, and the structure. Here total 6 pp bonds are present, and upon treatment with air it forms P4O10, and red phosphorus is not forming anything upon treatment with air. So these are the important points till now. And now we'll go for the electrical conductivity. So as we go down the group, the size is increasing. When the size is increasing, the distance between the valency band and conduction band decreases. So when the distance is decreasing, the electron can flow easily from the valence band to the conduction band. The electron can easily flow from the valence band to conduction band, and because of that reason it conducts more electricity. Okay, so as we go down the group, the electrical conductivity will increases. But in case of nitrogen family, it doesn't happen actually. So nitrogen to phosphorus, the electrical conductivity will increases, but from phosphorus to bismuth, the electrical conductivity decreasing. Okay, So this is because of bismuth is so here the explanation clearly not known, but the explanation what I read that from phosphorus to bismuth the metallic conductivity is increasing, okay, but the electrical conductivity is decreasing from the phosphorus to bismuth. Now we'll go for the, so just remember electrical conductivity from nitrogen to phosphorus it increases, from the phosphorus to bismuth it decreases, this much only remember. Next we'll go for the oxidation states. So we know that this 15 group elements maximum oxidation state is +5, but all the elements, among all the elements will shows +5 oxidation state except nitrogen. So nitrogen shows only in one case nitrogen shows +5 oxidation state, that is NF4 plus. Only in this case nitrogen shows +5 oxidation state. In other cases means it's not possible to show for nitrogen to show +5 oxidation state. And then for remaining elements like phosphorus, arsenic, Sb and bismuth, they can show +5 oxidation state. And this is the thing we have to remember about oxidation state. And the next thing is halides. So all these elements forms trihalides and pentahalides. Okay. So among pentahalides also, fluorides are common for all the elements, like phosphorus can form PF5, next arsenic F5, SbF5, bismuth F5. But when we talk about other halides like chlorine and bromine, only phosphorus forms PCl5 and PBr5, but other these elements also forms but not that stable. So there are two reasons. The one will be the d orbital contraction. This is because of the pore shielding, d orbital contraction. So among this PR5, it's highly unstable because of the d orbital contraction. And when we were talking about the down the group, we know that inert pair effect will be there, inert pair effect. So I am not going into the details, but the reason why phosphorus is possible to exist all halides, but it's not possible for other elements like arsenic, antimony and bismuth. It's not possible because there are two reasons: d orbital contraction and inert pair effect. So this d orbital contraction is due to the pore shielding. Next and we have this is called azide. So N3 minus. So what is the oxidation state of here? If they ask oxidation state, so here we have 3 nitrogens. Here the average oxidation state we have to take. So that average oxidation state will be -1/3. So this is also a very important point. For N3 minus, the oxidation state, average oxidation state is -1/3. So next we have next we are going for the oxides of nitrogen. So here we have NO2, N2O3, N2O5. So these are the very important. N2O5 is very important because so the many times questions have been asked for N2O5 and sometimes questions are asked on NO2 also. So here what we need to remember is how they exist. N2O5 how they exist, and NO2 how it exists, and then N2O3 how it exists. So these are the three things we need to remember. And other oxides also we have, like NO. This is one oxide. So these are the important oxides we have. And here what we need to remember among these things, NO2 is uh, inert towards air. It doesn't react with air, but NO and N2O, they react with air. So this point also we have to remember. So NO2 is inert, like towards air, but NO and N2O is not inert. So first we'll go for NO2. So how it exists means, like NO2 is having a feature that at equilibrium it exists in the dimer form. It exists as a dimer. So what is the dimer? So 2NO2 gives rise to N2O4. So NO2 exists as a dimer, that is N2O4. And then, so when we have a N2O5, we'll go for N2O5. So this N2O5, upon it exists as a NO2 plus and NO3 minus. Okay, and similarly N2O3, it decomposes into NO2 plus NO. So these three reactions are very, very important. Okay, so the NO2 at equilibrium exists as N2O4, and N2O5, it's a composition of NO2 plus and NO3 minus. They may ask a question, like they can frame a question like this. So N2O5 is a mixture of NO2 plus and NO3 minus, and N2O3 can decomposes into NO2 and NO. And the next concept is nitrogen activation. Nitrogen activation. So if you're doing some chemical reaction, if you joined PhD, or you're doing some project, so there we have to do some chemical reaction. For that chemical reaction, you use a nitrogen atmosphere. So we call N2 atmosphere as inert. So why this N2 atmosphere is inert? And we also talk about the Haber's process. So what is the Haber's process? So here we have N2 plus H2 gives rise to NH3. So this is the Haber's process. So this also we talks. So there are three main reasons why N2 is inert. Okay, the first one is we have a triple bond between the nitrogen and nitrogen. Okay, the bond order in the N2 is 3. So because of this triple bond, we need so much energy to break this bond. Okay, so much activation energy is required to break this bond. So because of that, it's like a time taking process. So because of that, N2 gas is inert. The second thing is the Homo and Lumo gap. Homo and Lumo gap in case of this compound is very high. Okay, when Homo and Lumo gap is very high, the electrons cannot go from the Homo to Lumo. So because of that reason, also this is inert. And then the polarizability is very less. The polarizability is very less. So these are the three reasons why nitrogen is inert in the chemical reactions. So we mostly use the nitrogen atmosphere for the chemical reactions. And then we'll talk about the Haber's process. So what is the Haber's process? In the Haber's process, we have nitrogen plus 3H2 gives rise to 2NH3. Okay, so this is also gas, and this is also gas, and this is also gas. And one thing about Haber's process, we need to remember that this is a reversible reaction. So this is whatever I am going to talk now, it's also very important because in Haber's process we use high temperatures and high pressures. Okay, so we just apply here Le principle. So according to the Le principle, when we increase the pressure, so the equilibrium way to shift, and when we increase the temperature, the equilibrium way to shift. Okay, those things also we have to remember. So means if we are talking about this one, hydrides. So here we have NH3. Sorry. Next we will go for hydrides. We have NH3, PH3, ASH3, and SBH3. Okay, so here the important thing is bond lengths and boiling points and the reactivity. So these are the three important things we need to remember, and these things are very easy also because these are all are related. So as we know that down the group size is increasing, so because of that bond length also increases. If bond length increases, boiling points also increases. But for nitrogen group, like nitrogen, phosphorus, arsenic, and we have nitrogen, oxygen, and fluorine. All this group shows some unexpected boiling points. So we have like a graph like this, and when we are talking about carbon, it shows like this, like this. So this is CH4, this is SiH4, and this is germanium H4, and this is SnH4. So this concept is working here. As we go down, the size is increasing, so Sn is having more size, because of that more bond length, so this is having a more boiling point. So this is a boiling point order. But when we see for nitrogen, this will be like this: 1 2 3 4. Sorry, we will keep like here, not here. And here this is NH3, PH3, ASH3, and SPH3. So in this case, the bond length order will be NH3 will be more, then SBH3, then ASH3, and PH3. And I will explain why also. And for oxygen also same, it also exists like this. This is H2O, this is H2S, and this is H2 selenium, and this is H2 tellurium. And similarly HF, HCl, HBr, HI. So in all these three cases, okay, the first element which is having a more bond length, if it's having more bond length means it's having a more boiling points also. This is the bond length order and also boiling point order. Okay, but the expected one means like it's supposed to be like ASH3, SBH3, and PH3 at last NH3, but here it's a different. So why it's like, if you see here we have the bond angle of 107.8 I think, and this will be close to 91.3, and this will be 91, and then this will be some 93.6. okay, like this 91.8, something like that it will be there. So the reason is, so nitrogen size is very small, the radius of nitrogen is small, so the hydrogen also small, so there will be a repulsions between the nitrogen and hydrogen because they are having small radius. So because of that the bond length will increases. So this is bond angle, not bond length. So these are bond angles. I forgot, I got confused. These are bond angles. So the bond length increases in case of, because of these repulsions. Okay, so when bond length is increasing, the automatically bond boiling point also increases. Okay, so the same effect will not be so much in case of pH3, because this is having a moderate size. So because of that, the repulsions will not be that much in case of pH3 as we compared with NH3. And SbH3, ASH3, they have bigger size, because down the group size is increasing. Since they have bigger size, they will be having a more boiling points. Okay, this thing we have to remember. So in these three families, in these three groups, like fluorine, oxygen and nitrogen, the second element is having a least boiling point, and the second element is having a least we can say bond lengths. Okay, this we have to remember. And next we have yeah, and here we can also talk about the hydrogen bonding. Hydrogen bonding. So here we can frame a question like A NH3, B water, C we have a HF. Okay, these are the three compounds here we have. And the question is like which one requires more energy to break XH bond here. So here X equals to nitrogen, oxygen and fluorine. So this is the question, like we have three compounds NH3, H2 and HF. Which one requires more energy to break XH bond? So here we have to remember that here we have to talk about the hydrogen bonding. So we know that if the higher the electronegativity, okay, if higher the electronegativity, the strength of hydrogen bonding also increases. Okay, with respect to hydrogen bonding, if we talk up with respect to hydrogen bonding, okay, so here in case of HF there is a strong hydrogen bonding and it requires more energy to break. So the order will be C, B, A. So this will be order. And if you're talking like hydrogen bonding versus covalent bond, so then the criteria will be different. So when we are talking about this one FH, so this is the hydrogen bonding, okay, of HF, and we also have a FH. So this is the covalent bond here, and this is the hydrogen bonding. Always remember, covalent bond is stronger compared to hydrogen bonding. Hydrogen bonding is weaker. So we require less energy to break this bond. It's around 163 kilocalories of energy is required to break this bond, but in order to break this bond we need 574 kilocalories of energy. Always the hydrogen bonding is less stable compared to the covalent bonding. Okay, so next important topics are inertness of N2 and Haber's process. So when we are doing some chemical reaction, in that chemical reaction we use nitrogen atmosphere, because nitrogen atmosphere is inert in nature. So why this is inert? There are three reasons we have why we say that N2 is inert. The first one is the bond order between nitrogen and nitrogen is 3. So if we need to break this bond, triple bond, we need so much of activation energy. And because of that reason this is inert. So this is the first thing we need to remember. The second thing is the Homo and Lumo gap is very high in this case. High. So this is also one reason why it's inert, because if Homo Lumo gap is very high, the electrons cannot go from the Homo to Lumo. Because of that, this is inert. The third thing is low polarizability. So these are the three important things we need to remember why nitrogen is inert. Then we'll go for the Haber's process. So what is the Haber's process? We have 2 moles of nitrogen plus 3 moles of hydrogen. These both are gases, and we have a 3NH3 2NH3 plus some energy, some heat will be releasing here. Okay, we can say this is the exothermic reaction. This is exothermic reaction. Now, so the question is, we are using a high temperatures and high pressures in the Haber's process. Okay, another thing we need to remember, this is a reversible reaction. So if we apply the Le Chatelier's principle, so according to this Le Chatelier principle, if the reaction is exothermic, and then further if we increase the temperature, what is happening here? The heat is increasing. Okay, in order to decrease the heat, the equilibrium shift towards your left hand side. Okay, so this reaction is already reversible reaction. Reversible means like we will not expect much yield. You will get less compound of less amount of NH3, because the reaction is reversible reaction. So there is possibility that this also forms, and further the ammonia also come back into these gases. This is the reversible reaction. But still we are using high temperatures in this reaction. Without high temperature, this reaction doesn't goes. But according to the Le Chatelier principle, if you use high temperature, the equilibrium is shifting towards your left hand side. Then, and here we are using high pressures also. High pressures. So as we know that pressure doesn't have any effect on the equilibrium constant directly, but with respect to volume there is a effect. So now I will tell why we are using a high temperature. So this high temperature is not for the reaction. This is not for the reaction. This is for because nitrogen is inert in nature. So in order to make them, and as I said that we need more activation energy to break N2, means there is a triple bond. Because of that we are using high temperature, not for the reaction, not to the increasing the reaction yield like that. And we are using high pressure to overcome unfavorable equilibrium constant, to overcome thermodynamically unfavorable equilibrium conditions. So what is the meaning by unfavorable equilibrium condition? So it's already, we know that it's already reversible reaction, and according to the Le Chatelier principle, if we use high temperatures, the equilibrium is moving towards your left hand side. But this can be overcome by using high pressure. How we can overcome this? By using high pressure. But I said that pressure doesn't have much effect on this equilibrium constant, but with respect to volume there is some effect is there. So we know that if volume increases, pressure decreases. This we know that. Okay, when volume increases, we know that the equilibrium moves towards where more number of gases are there. More number of gases are there, that to that side the equilibrium moves. Okay, when pressure increases with respect to volume, that means volume should decreases. In that case it moves towards less number of gases. Less number of gases. You're understanding, right? So we know that volume is inversely proportional to the pressure. So when we increase the volume, that means pressure is automatically decreasing. In that case, the equilibrium shift towards where more number of gases are there. If you see in this Haber's process, the equilibrium is shifting towards your left hand side. And when volume decreases, in that case pressure increases. In that case, the equilibrium shift towards where less number of gases are there. And as we go from the left hand side to right hand side, here we have less number of gases, two gases. So because of that reason, here the equilibrium shift towards your left hand side. So this is we are using high pressure because to overcome this unfavorable condition, unfavorable equilibrium condition. Unfavorable equilibrium condition means like we are using high temperatures and it's moving towards your left hand side. In order to overcome this, we are using high pressures also. And then we have another thing here, promoters. So we use promoters in the Haber's process. So what are the promoters? We have two promoters, like MgO2 and SaO2, sorry, MgO and SaO2. So these are the two promoters we have. So the role of these promoters are to activate the catalyst. So what catalyst we use in the Haber's process? We use a iron catalyst. So these promoters activates this iron catalyst and it further makes the reaction is faster. Okay, so this is about the inertness of N2 and Haber's process. And here why we are using high temperature and high pressures. If they ask why we are using high temperature and high pressures, we can say that because of the inertness of nitrogen, not because to increase the yield like that. Okay, and then we have enzyme called nitrogenase. So this is biologically very important. So this exists in the plant's roots and it converts the nitrogen into NH4 plus. So this also we have to remember. So then these are some important topics, some important points about the nitrogen. And then we'll go for in the nitrogen solely we will go for structure of N2H4. So what is N2H4? N2H4 is the hydrogen. So this is also very important. So if we see the hydrogen, it adopts the Gauche conformation. Gauche conformation, and they may ask what is a point group for this Gauche conformation, and it exists like this: nitrogen, hydrogen, hydrogen. So this exists like this. Okay, this is the structure of hydrogen, and it adopts the Gauche conformation. And then this can be prepared. I think preparation methods are not required. Just remember the hydrogen structure. And as I said, that next important one is azide. So these azides are also very important because this we use as a detonators because these are highly explosive in nature. Because of that we use this one as a detonators. So because of that it's very important. And the N3 minus, here oxidation state is average oxidation state is 1/3. Okay, so when why it's a very explosive, when we expose this one to the air, it releases NaN3, it releases Na sodium plus and nitrogen. So because of that it produces the nitrogen. Because of that it explodes in the atmosphere. And we have another compound that when we treat N3 plus N2, in that case we will get a N5 plus. Just remember about a hydrogen, the structure it exists in the Gauche conformation. About azides, we use them as a detonators, and the oxidation state of azide, and how azides are acting as detonators. Because when this exposed to the air, sodium azide, when we expose this to air, in that case this releasing sodium and N2. Because of that it's acting as a detonators, and N3 plus N2 gives rise to N5 plus. Almost all pentahalides of this group are Lewis acids. So if you have watched a video in my, like, I have made a video on the non-aqueous solutions. You please watch that video. So there I have explained about SBF, SbCl4, SbCl5 and those things. Okay, that's why I'm not going here in the details. Now we're going to talk about the PCl5 reactions. This is very, very important. So when we have a PCl5, when we treat this with a Lewis acid, it forms a PCl4 plus. Then PCl5, when we are treating with a fluoride donor, it forms a PF6 minus. And when we treat PCl5 with the NH2, nitrogen having compounds, it forms a PN bond. So this is very important. That is, we call it the Pasper-Gene. Okay, the questions will be many times questions have been asked on this Pasper-Gene. Okay, so here what are the Lewis acid we can take? Let's take that. If they ask what is the product of PCl5 and BCl3, so we know that BCl3 is the Lewis base. Just remember, just by heart, these three things, that when we are reacting PCl5 with Lewis acid, you are getting PCl4 plus. When you are treating with F minus, we are treating this one, like that. And simply you can write here, anyway you will get here PCl4 plus, and this chlorine goes from here to here, and BCl4 minus. So this is the thing we have to remember. Next, when we treat with PCl5 with the KF, in that case we get a PF6 minus. We can also write this one as a K PF6. And when we are treating this with the NH4Cl, we'll get a N double bond PCl2 N. This is a cyclopasine. And another important one is PCl5 upon treatment with water, it forms POCl3. Okay, and upon treatment with the P4O10 also, it forms a POCl3. So here 1, 2, 3, 4, 5, these 5 reactions are very, very important. Okay, if it means like if they ask PCl5 reactivities, whether they can ask on the cyclopasine, or they can ask on PCl5 reaction with BCl3 or KF, or with this water and P4O10. So these are the important reactions of PCl5. And also we have phosphorus oxides. We have P4O6, P4O10, P4O8 and P4O10. So this is formed when white phosphorus upon treatment with air, it forms P4O10. So these are all having a tetrahedral shape. So the structure will be, if you can remember P4O6 structure, then it's very easy to remember other structures. So keep 4 phosphoruses and keep PO bond between all phosphorus. Now how many oxygens are left? 2 oxygens. So this is 1 oxygen and this is a second oxygen. Okay, this is a P4O6. For P4O7, 1 extra oxygen is coming. That oxygen is keep here. This is P4O7. For P4O8, this is the structure. For P4O10, this is the structure. Okay. And here we have two more oxides like P2O6 4 minus and P2O7 4 minus. So these are belongs to one kind of oxides where we have POP bond, and these are the if you see this structure, it will be like this: P, P, oxygen, oxygen, oxygen. So this is the structure of P2O6 and P2O7. Always remember, when you have odd number, in that cases, definitely you will get a this like peroxy kind of, like we can say POP bond will get like this, P4O7. And till now I hope I covered most of the things, and we have a phosphogenes. I think phosphogenes are well known in the YouTube. There are many videos are available on phosphine, and even if I make also, I may not get much views for that. Like we have nitrogen halides. So we have NF3, NCl3, NBr3, and Ni3. It's very simple and it's not that important also, but here we need to remember few points. So NF3 is stable, but these all three are unstable. These are highly explosive in nature. Highly explosive in nature. And here what important point we have to remember is the nitrogen oxidation state we have to remember. So here nitrogen shows -3 oxidation state. In these two cases nitrogen shows +3 oxidation state, and this one we can say that this is a non-polar, because nitrogen and chlorine electronegativity is almost same. Because of that reason it's a non-polar. But in case of NBr3 Ni3 it shows +3 oxidation state. In case of sorry here +3 and here it's -3. In case of NF3 it shows a +3 oxidation state, because if you see the polarizability, it will be having a partially negative charge and it will be having partially positive charge. It shows +3 oxidation state. In case of NBr3 Ni3, nitrogen is having a more negativity compared to the bromine and iodine. Because of that it shows a -3 oxidation state. And then NF4 plus also possible to exist. So I said that before, when I start this lecture I said that NF4 or NF4 plus is the only compound where nitrogen exists in the +5 oxidation state, and this we can prepare by treat with NF3 with 3 moles of 2 moles of fluorine and SbF3. Here we get a like it will get like this NF4 plus and SbF6 minus. This reaction is very important. We have to remember this reaction. So here what points to remember, that in case of NF3 it exists a +3 oxidation state. In case of these two it exists a -3 oxidation state. And other halides can shows AsCl4 minus and SbF5 minus 2. So these are also possible to exist. And here what we need to remember is the point groups of these compounds are very important. So SbF5 exists like this. So this will be a C4V point group, and AsCl4 the structure will be like this. This also comes under the C4V point group. So except like now we are going for the pentafluorides. Means I am not telling in order, so what are the points I am remembering, so those points I am explaining here. So except PF5, so what is the PF5 structure? Trigonal bipyramidal structure. Except this, other fluorides like we have SbF5 and AsF5, these are exist in the, we can say that these exist in the tetrameric form. Okay, and if we see the structure of SbF5 tetramer, and this structure is very important they may ask, like the structure will be like this: 4 SBs are there, and each SB is having one bridged fluorines, and then each is having a 4 fluorines like this. Okay, so this is the structure of SbF5 in the tetrameric form. They may ask a question that how many fluorines are in the bridge. So total 4 bridged fluorines we have. Okay, and SbF, Sb bond exists in this case. So this is also important point. And this we know that is very well. The PCl5 in the solid state, it exists as a PCl4 plus and PCl6 minus. The reason behind this one is when you're talking about a solid state, there should be a proper crystal packing which should be there. Then only we can say that is a stable solid. So PCl5 in this state, the packing pattern is not that good compared to PCl4 plus and PCl6 minus. In these two cases, the packing efficiency of PCl5 is good in these two cases. So because of that reason, in the solid state, PCl5 will exist as a PCl4 plus and PCl6 minus.